Okay, so this shouldn't take that much time because there's not much logistics actually. I think I've already covered this. Basically, today we're in a very special state in computer architecture. There are very interesting trade-offs like this that we're going to examine in the next lecture. This is the energy of a complex floating point addition. This is the energy of a memory read or write. And you can see the orders of magnitude difference, right? It's 800x here. Okay, you can always exaggerate the numbers and make it 3 orders of magnitude, right? And that is true actually. This is becoming worse. Although you can play a lot of tricks, it's not really 1000x if you really optimize it. It's between 2 or 3 orders of magnitude. That's actually recently I was at the design automation conference where people were giving numbers from their AI accelerators and machine learning accelerators, and one person was generous enough to give the number 160x in terms of the relative energy consumption of a memory access in their machine learning accelerator compared to a single floating point multiply and accumulate, which is a complex operation. 160x is a big number. So whenever you see a disparity like this, it's always good to ask the question, does it really make sense to bring data into the chip to process it, right? Especially if you're not taking advantage of the locality of data. For example, if you're doing a lot of random accesses, you're not going to reuse the data again. You just want to add 2 numbers and write the result, and you're never going to touch any of them again. Does it really make sense to do 3 DRAM accesses, 2 for reads and 1 for write, and then do a single, very simple in the sense of energy, operation like this, and waste 3 times 1000x, as opposed to pushing that operation to the memory, which is a completely different model, of course, and we're going to cover that in this course. So this course is going to cover a lot of different models, hopefully. So past systems, okay, I don't know why microprocessor went away, right? Apparently it's not important. Clearly microprocessor is not the only thing. There are lots of different processors that we have today. That's probably why it went away, so that it gets replaced with this thing. So clearly we're at a very interesting space today. We have all these modern systems that are very heterogeneous. So basically, the key goals of this course is hopefully enable you to understand how a computing platform works. Clearly we're not going to cover every single component because it's very hard to do that, but we're going to take some examples from different components, especially important issues like this. Hopefully understand how decisions made in hardware affect the software and programmer as well as the hardware designer. I think we've already been doing that actually nicely, so let's keep that spirit. Think critically. I think this is, if you don't get anything else out of this course, if you get this one, I think this is going to be useful for your entire life, because I think whatever you do, thinking critically will enable you to do something bigger. And I think hopefully you can think broadly across the levels of transformation that we've been thinking of. And hopefully you can better analyze and make trade-offs in design. And this is basically what we will do. You'll apply this, hopefully all of this, in several lab projects and homeworks, and hopefully during the class as well. Well, I think I already introduced myself, right? I think so, yeah. But I haven't introduced the TAs. Juan is really the person who's heading the TA team, and we have a lot of TAs. They have different roles. As you can see, not everyone is here, so I'm not going to go through this list. But you can consult any of them, and they're going to be helpful with the labs. These are essentially my PhD students and postdocs. You can think of it that way. So it's good to get to know them and their research as well if you're interested in this area, certainly. And they're doing, actually you can recognize some names. Minesh was the first author of the Reaper paper, for example. Okay, so basically the major high-level goals of this course, hopefully you will understand the principles and the precedents, both. And based on such understanding, you can evaluate the trade-offs and develop principle designs, develop novel out-of-the-box designs. That's the goal basically at some point. And I think we already kind of started doing that. And I've already said this, I think. And of course, computer architecture, that's the context. And as I said earlier, this course might seem like computer hardware. Whenever people think about computer architecture, it's interesting, people get different reactions. Some people think it's software architecture, which definitely is not what this course is not about. But some people think this is completely computer hardware. And I don't like that thinking, because today, as we discussed last time, right, there's no hardware-software boundary. People are breaking those boundaries much faster than a lot of things are happening, right? And as I said, you'll be much more capable if you master both hardware and the software, right? Traditionally, software companies are becoming hardware-software co-design companies. And hardware companies are also becoming more software-hardware co-design companies over time. and the interface between them, of course, right? You can develop better software if you understand the hardware, you can design better hardware if you understand the software, and hopefully if you understand both, you can build a much better, much more efficient computing system. Whatever metric you are trying to optimize for, you can optimize for much better. And we've already discussed this over here. So, okay, you asked about required background. I think I already answered questions. Digital circuits, even though it's required, I think if you have the right mindset and if you do the right preparation, people have been successful even without having that background. Since this is a master's level course, I think the requirements are more relaxed compared to a strict bachelor's level course, for example. I think basically this is important, open mind. The programming labs will not be as easy, although it's going to be easier than last time because we're going to get rid of the Verilog labs. Although some people who like Verilog may be disappointed, sorry. At some point I think Verilog design also needs to change because there are some idiosyncrasies I think in Verilog and system Verilog. I think the conceptual abstraction level needs to be improved in Verilog also, and people are trying to do that. People are trying to, for example, go from C to gates, but that's a very tough thing. Getting to a little bit higher level language to program hardware would be better. But until we do that, I think we don't have the Verilog labs for now. Okay, basically what I expect from you, certainly required background. I think having an open mind and being willing to cover up the gaps that you may have to understand things would be very, very useful. Learning the material thoroughly, I think it would be good. I think by doing this, I mean, there's no required thing in a sense, right? Lectures are not required, readings are not required. Well, I guess they're required in the sense that if you want to get a grade, you should do it. But attendance in the lectures are really not required. But I think you will benefit from attendance more than if you don't. But if you don't come here, that's also fine. You can watch the video if you're interested. But I think participation is very useful if you're here. Okay, I mean this is obvious, I think. So this will be a hard but hopefully fun and informative course. I think you're already doing this. Ask questions, take notes, participate. That's very good. Like today, I was intending to cover more than what we're covering right now, but that's okay. I think we dug deeper and we talked about a lot of different ideas. I think that's a different way of covering things. I think performing the assigned readings will be important. I think some of them will be in your homework. I think this I would recommend, even though it's not required. I would recommend starting early, especially important with labs. Starting early is a good one, okay, we'll discuss the labs when the time comes with the first lab, clearly. And if you want feedback, come to office hours. You can always contact me or the TAs. We'll arrange some time, and the office hours will be published at some point. It's not ready yet, but they will be published. This could be useful for labs, homeworks, or some of the concepts that you want to know about. Some of the lecture sessions will be also the lab/discussion sessions, essentially. So you can actually ask questions over there too. I like this quote over here by Pasteur: "Chance favors a prepared mind." So you may actually have a really great opportunity in front of you, but you may not realize that you have that opportunity because you're not prepared to see that that's an opportunity, right? I think that a lot of research works this way, actually. It's really preparation plus some luck that you have. If you're not prepared well enough, you may not even notice that you're lucky. But if you're prepared well enough, then you will see the opportunity, and when the luck comes and hits you, you will actually take it. I think that's what preparation is all about for research. Doing all of the reading these papers and everything leads to some background that enables you to pull the luck to yourself whenever that luck is there, right? And this is especially important for an architect, because as an architect, you're always looking for the future, right? You're trying to enable some future. And if you're prepared, you will see the problems, for example. Like refresh is one example I like to think about. Memory controllers, which we will also talk about, is another example, again, that I like to think about. New technologies, enabling new technologies. It requires having some preparedness to really see the technology when it's presented to you. If you're not prepared enough, for example, if you don't have the right mindset, right thinking, whenever a technology is presented to you, let's say phase change memory, you can easily dismiss it. Oh, that's not ready yet. But if you have the right preparation, you can say, okay, this technology looks interesting. How can I really make it work 10 years down the road? Right. I think that's what he really meant to say over here. And that's what it looks like. Okay. So I think how you prepare and manage your time is very important. There will be many lab and homework assignments, so they will take time. And I think actually some of the homework assignments you can find in the last year, including the solutions, right? So all of them are online. Even though some assignments will be slightly different, clearly. I'd recommend doing them yourself, clearly, but yeah. I'm not going to be a police. Okay.
So how much time do you expect this course to take, apart from the 6 hours lectures a week?
Yeah, I don't know, actually. It really depends, especially since we're getting rid of the Verilog labs. It's very hard to guess right now. So, for example, if you didn't know Verilog very well, it could easily take a lot of time. And there were students who didn't know Verilog in the past. They did the Verilog. They really enjoyed it in the end, but they said it took a lot of time. You could probably ask them. But if you enjoy it, I think you can do it fast, hopefully. Okay, so I think this is the more important part maybe. It'll be a heavy course, but I think you'll learn a lot for sure. And it's not just, I think, how computers work. It's probably this aspect that's more pervasive. Even though you may not be able to appreciate it right now, I think in the best courses that I've taken, the courses really enable you to think differently. And I enjoy that aspect a lot. Even though you learn a lot about a particular technology and platform, let's say, it's really the thinking differently part, that thinking critically part, that enables you to do something even bigger than this learning part. Okay, so now we have to talk about grades. This is my least favorite part. I'm not sure if the grade focus of a university is the best focus, but I guess that's the system we have. So you can always question the system critically too, right? Basically, this is what we have. We have a midterm exam, final exam. You can see examples of this online. We may follow a different structure this time. It's not guaranteed that you will have something very similar. Project assignments, as I said, that's the most important single part of the course, as you can see. And I think you'll learn a lot from the project assignment. And as I said, this is going to be high-level language-based. And homeworks, again, you learn a lot from homeworks. These will be paper reviews as well. Does it sound good? I assume this is correct, right? I didn't double check, but we didn't change it recently. Okay, more on this later, clearly. Okay, I think I've already said things like this, basically. Basically, we'll learn a lot about processor, memory, and platform architectures, and fundamental operation principles and design trade-offs, but also key current and future issues. Basically, we're going to look always, have eyes everywhere. And I think this is the lab part. This is more the lecture, discussion, homework part, but this is really the lab part. As an architect, you really need to figure out how to evaluate ideas. And a lot of the ideas we've discussed, and we will talk about, we'll have a lecture on how to evaluate ideas, like methods. But simulation is really a key tool of the architect. Because it's very hard to implement every single idea that you have in hardware, especially if it changes hardware, right? It's very costly, it's very time consuming, you have to get it perfectly correct. But simulation enables you to dream much better and much faster, because you model it. Maybe you don't model it perfectly, but you model it just enough to get a good idea of how much the idea will benefit some particular metric. And this is very critical, I think. If you haven't done simulation in the past, this is really important. Any simulation is like that, actually. If you do weather simulation, for example, you have a trade-off between speed, accuracy, and flexibility. Right? You can get very high speed by losing a lot of accuracy. Right? Or you can get rid of flexibility such that your simulator is not adaptable to certain conditions, for example. But then you may not be able to model everything you want in weather, right? So simulation is a very general concept, but we will in this case look into simulation in architecture. And I think this is really important. Our main emphasis will be on functionality, but sometimes we'll also look at efficiency as well. But more on this later also. So hopefully you'll get to implement some ideas that maybe we'll discuss in some of the simulators. Okay, this is going to be fun. So radar, for example, the radar idea that we discussed is implemented in a simulator, right? That was not implemented in a real system. The retention time measurements that I briefly showed you, they were done in an FPGA-based platform. You have an FPGA, you build a simple memory controller to test the retention time of different DRAM cells, and you can measure that. That cannot be done in simulation. Well, Okay, I'll take it back. You could model retention times in a simulator, at a circuit level simulator that gives you the leakage. But then you need to get your parameters very, very nice and accurate to really represent the device. Now the question is, how do you get your parameters accurate? You really need to have some real data as basis. So you really have to do what we've done if you want to really have a better simulator also. That's usually how the simulator loops work actually. If you really want to gain confidence in your simulator, you implement at some point the ideas in real hardware, and then you calibrate your simulator based on the real implementation. Now of course, if you're considering a completely different design from the real implementation, now you need to be careful again, right? How do you actually modify the simulator and really trust the results that is provided by it? So there's a lot of art that's involved in simulation also. Okay, this is the course website. Several of you asked for it, but it's basically the same architecture website that we had last year, except it's not fall 2018, it's fall 2019. And everything will be posted over there. So I would suggest checking this frequently. There will be announcement and due dates. We'll usually announce stuff on Moodle also, so you'll get email messages also. Check your email frequently also. So this is homework 0. That's due next week. I think the due date is correct. Yes, 26th. Basically, this is very simple. This is information about yourself, and I think you'll submit it via Moodle. Is that correct? A PDF. PDF, please. No documents. No docx. Even though I use that, it's better to have a portable document format, which is what PDF stands for. Okay, so this is basically everything is predicated on homework 0. So if you don't tell us about yourself, then we're going to assume that you're not taking the course. Is that fair? I hope so. Okay, so this is a very rough outline. This will become more clear later on, starting next week. Basically, we'll have a few required review assignments as part of the homework. Essentially, these are homework pieces. We'll try to do homeworks more fine-grained and smaller homeworks. Let's see how it goes out. Basically, you can expect a homework that's due approximately 2 weeks, and interleave labs that are due approximately 2 weeks. Although this may change also. So keep this in mind for now. This is the real thing will be the website. And I think I would like you to do the labs and the homeworks. So I'm relatively flexible, especially on the lab deadlines. In the past, actually, at some point, we allowed the labs to be submitted even after the course. I wouldn't recommend doing that. I think the best way to do the labs really is to try to submit them as the labs go. Because if you try to, let's say, violate all the deadlines and do all of the labs in the last minute, that's going to be a lot of burden. Sometimes I think engineers are very happy doing that, but it's not a good mindset to be in, I think. don't. So I think respect the deadlines, even though my eventual goal is for you to learn, and for learning you need to do the labs. And if you need some more time, I'm happy to accommodate that time. But I think pushing that too far is not good for your learning in the end. That's why I don't like courses where you really are evaluated based on a single exam at the end, right? I think that's not a fair way of evaluation of your knowledge, frankly. But I mean, I guess some other people like it. Okay, I think that's all of the course logistics I have. Any questions on this? Yes?
Is the exam dates already available?
Oh, we haven't, yeah, it's not already available, but we'll make them available soon. And sometimes, actually, in the past, we've taken some votes as well in terms of what should. So there's a relative flexible. Although it's a bigger class, so we'll see how flexible we can be in that case. Yes.
Do you suggest any other course that would be complementary or interesting in computer science?
In computer science, you said? That's very general. I mean, there are a lot of good courses, I think, but related to computer architecture. Let me think about that, and I'll get back to you. You mean this semester?
Yes.
Okay, I have to look at this. What's this semester? But if you send me an email and send me a list of courses that you think are relevant, then I can respond to you and provide suggestions. Yes.
Is the final exam in the end term we're doing the exam session?
Yeah, so traditionally in this course we've had both of the exams in class. Meaning that the final exam, the expectation is that it's going to be maybe the last day of classes or the day before that. And midterm exam is somewhere in the middle, let's say maybe late October or November. Yeah. Yes?
Is there any provisional schedule of the topics that we will cover?
Not fully at this point, but you can take a look at last year, although things may change compared to last year. So keep that in mind. It's not going to be exactly the same. But I mean, you can guess first exam will cover a lot of memory, for example, because we're going to start with memory and talk about memory systems. I mean, you saw the example of refresh. I think in the past we had a question on refresh, for example, which is not that hard, I think, but like you can expect some question that's similar to what I just described, although that's a bit easy. The 1 exabyte DRAM question, right? They can take a look. I can easily say that it's going to be a lot of memory topics, the first midterm, and then the second part is going to be more multiprocessor, heterogeneous architectures, acceleration. Although we may need to reorder some things once in a while, depending on my travel schedule and other things. So there's a lot of dynamic reordering. So the best systems work with dynamic scheduling, actually. We can form a static schedule, and that static schedule is usually not good. That's what people have figured out in designing computing platforms. The compiler forms a static instruction schedule. The hardware does something completely different, right, underneath. It reorders a lot of the accesses. Yes?
If we don't do Verilog in the lab, so are we mostly doing software or hardware design? Or like,
Yeah.
what are we doing in the labs?
Sure. Basically, you're modeling hardware.
Modeling hardware.
Well, Verilog is also software.
With software.
Exactly.
So like, what like
you'll find out.
so like with C or with
Exactly. So exactly with C.
Okay.
I mean, there's no reason why you cannot do it in Python, but we use C for grading.
Okay.
But essentially, you're doing exactly what.
Okay.
I mean, Verilog is also modeling hardware, right? It's not real hardware in the end. But it's a very lower level of abstraction that's very close to how hardware exactly operates. But for example, if you model the hardware at a higher level of abstraction, you don't need to, you can basically say some operation takes 20 cycles. Let's say you don't model a multiplier, you don't build a multiplier, but you get a multiply instruction. What you do is you add 20 cycles to the latency of that instruction, so the next instruction that requires the value becomes available 20 cycles later.
Okay.
So there's no modeling of the multiplier in that case, right?
Okay.
Does that make sense?
Yeah.
So that makes a lot of things easier, clearly.
Yeah.
Now you can do much faster evaluation because you don't need to go and model every single thing. You don't even need to do the multiplication, actually.
Okay.
A lot of the software simulators work by not modeling exactly what goes on. Then you'll see that. Yes?
Are the labs considered a project when it comes to grading, or are those two different things?
Say it again. Labs considered.
Such as the project work when it comes to the grading, or are those two different things? We're going to have separate projects.
No, there's no project. Basically, this. If you look over here, yeah, labs are the same as project, basically.
Okay. And do we complete the labs here in the building somewhere, or is it like a project we can do?
No, you can do it on your own. Actually, it's relatively flexible. There's no. You can do the software on your own laptop, for example.
Require some sort of hardware here in the building.
No, it's relatively low overhead in that sense. You can do it on the tram. Yes.
So the final exam is in session exam, or is it at the end of the
It's during lecture, in session basically. Probably the last day of class or the previous day. That's the expectation at this point. Anything else? Okay. Well, I'll see you next week then.